Morning, everyone. So this will be our last lesson in Chapter 2 on ionization energy. Hopefully you've had a chance to try out the electron configuration model for yourself. Again, that is a sort of a new model. We took the Bohr model, we took what was good about it. Bohr had already figured out that different shells are quantized. Electrons are either on orbit 1, orbit 2, orbit 3, but we've started seeing in this model, electrons actually aren't in orbit around the nucleus. They actually occupy these orbitals. Each of the shells that Bohr said can be subdivided in different layers that we labeled as S, P, D, and F. Yesterday we talked a little bit about orbitals. We talked about how each shape, the S, P, and D, F, have a different region that's sort of marked off. And like the funny cat analogy, the cat doesn't need to decide whether it's dead or alive until you make a measurement. In the same way, although there is a high chance of finding electrons somewhere in the orbital, the electron, as a sort of wave-like nature, doesn't really need to take on any spot unless you actually go looking for it. Again, sort of the implication there is somehow we've screwed up the system by looking for it, by making an observation. We've actually changed it from what it was already doing, but we just try to make do with what we find out from there. This last part here, this is actually a nice evidence for us to actually have different subshells. So I'm just going to give you just a simple sort of comparison here. Let's take an element here. Let's do carbon as an example. So carbon, if you look at your periodic table, carbon has 6 electrons. So we have the 2 on the first shell, 4 on the outer shell here. We did a little bit of this when we introduced the Rydberg equation. What we're going to do is we're going to artificially come and we're going to be removing electrons. So I'm not saying carbon naturally wants to do this, but this is, I have my carbon, it's just sitting there, maybe graphite, maybe diamond, whatever form it is, and I am applying whatever energy that you need to actually completely rip off the electron. In this case here with the simple Bohr model, you can only grab the valence shell first because like layers of an onion, the outer layer is exposed to you here. We're going to take a pair of tiny tweezers, grab the first electron that we see, and try to remove this electron. This process of taking carbon and pulling off an electron will eventually be related to our concept ionization energy. I'm just going to call this IE for now. So if this were the picture, there's my carbon atom. If electrons really were I have 4 electrons all on shell number 2. If I compare the first electron that I remove to the second electron that I remove to the third electron that I remove, because this picture sort of suggests the electrons are all identical. They're all on the same shell number 2. They're all sort of equal distance from the nucleus. I would imagine, although the ionization energy might be different between these ones here, I would imagine even if they did change, they're going to be comparable. They're going to be close together, and that it's not going to be one that's suddenly much higher than another one. So that's the model that the Bohr model predicts. If you do the electron configuration model, that energy level diagram for the same carbon atom, we have shell number 1, shell 2. We won't even need to go up to shell 3 for this question, but shell 1, we have our 1s orbital. We do the upspin, downspin. Shell 2 was where we started seeing that subdivision. Remember, every time the S shell shows up, we only get one of them. So we have floor number 2, but it's S kind of room. We actually learned in an electron configuration model that shell 2 is actually separated into these 2 sublayers. Be really careful, each of these rooms themselves is an individual orbital. And in this case here for carbon, again, this was already one of the parts that were inconsistent. Because electrons want to off-ball, electrons want to build up lowest energy first, the 2s is actually going to have single and paired up. So it's sort of like the Bohr model, instead of going single, the first 2 electrons should technically be paired up. But again, we still do the Bohr model like this because this is going to help us in chapter 4. So we'll keep them single. I know that's not quite correct. We'll need to modify that. But based on our electron configuration model, we have a 2s2. We do our Hund's rule for this latter part here, 2p1 and 2p2. So there's the 6 electrons. We can practice an electron configuration, 1s2, 2s2, 2p2. Right? If I add up all those superscripts there, it ends up giving 6. If I ask you how many orbitals have at least an electron in it, there's 1 2p orbital. This one is the second 2p orbital. 2 2p orbitals have an unpaired electron in there right now. So be careful. Pauli says each of these orbitals as rooms themselves, each room can only handle 2. Let's think about doing the same process of ionization energy. You come in with a really microscopic pair of tweezers, just like layers of an onion, you're not allowed to tackle anything on shell number 1 that's too close to the core. We're going to tackle things that are on shell number 2. Our electron configuration model does a little bit better than the Bohr model. It actually recognizes that although we have 4 electrons on the outer shell, it doesn't mean all 4 are equal distance from the core. In fact, what it looks like here, because the 2 p's are higher energy, if you remember the shapes of the p orbitals, let's see if I can draw a 3D diagram here, x, y, z, the shapes of the p orbitals were dumbbell shaped. Px was a dumbbell along the x direction, py was in and out in the y direction. If I have a pz, it's also 90 degrees from it. Those p orbitals are actually further out than, say, where the s orbital are more spherical in shape here. Remember, these are that wave function squared. It's basically a probability of where I might find the electron. So just like the cat analogy, the electron really doesn't need to take on any location. When I go looking for it, I would expect to see on this floor here 2 electrons pop up somewhere in that 2s orbital. I would expect 1 electron to pop up. Let's say the red one was the px, so I would expect 1 electron to show up here, and the other electron show up, let's say 2py, so this one's going to be the other p. So that's what the picture looks like. You'll notice there are parts of the p orbital that are actually further out from the nucleus than the actual s orbital. So what that would imply to me here is if I came along with a pair of tweezers, remember when we remove electrons, we do that special order, p, s, and then d and the f. We really don't need to worry too much because we haven't gotten to the d's or f's yet. So pretty much the p's come off first. Yep, those were the last ones that I added. The p electrons should be easier to remove than the s electrons because the p electrons are further out, right? They're less attracted to the core. So when the electron actually appears in the far side of the dumbbell, that electron is much easier to pull off than, say, the s electron. So this actually becomes a nice evidence for us for the subshells. If it really were like Bohr said, where everything was all equidistant, we'd imagine all 4 are about the same difficulty to pull off. But when we actually do this is called successive ionizations. I come back again and again. I try to ionize 1 electron one by one until these electrons come off, and we track how much this ionization energy is. So we will see ionization energy a little bit more in the next chapter. There is a reason why we're seeing it just sort of introduced to you here. Make sure we know this definition for ionization energy. So ionization energy, we're going to shorthand it IE. Super important when you're defining this here. Obviously, if you have an infinite amount of energy, you can pull off any electrons, there's no problem. Ionization energy is sort of the barrier value. It's sort of saying this is the minimum, this is the smallest you can pull, and the electron has just happened to come off, versus, oh, I pulled much harder, it would have come off anyways. This one here has to be the minimum. So ionization energy, if you're defining it, you have to have this word here, minimum. It's the minimum energy needed to remove. We are pulling off electrons. In chapter 3, we're going to come to another trend where we're adding electrons, but that's given a different name. In this case here, IE is pulling off electrons, remove an electron. Right, that's based on this picture here. Your atom was minding its own business. It already had its electrons. You grab the first electron, the outermost electron that you see, and you find how hard is the least that you can pull for this electron to come off. Turns out if you just do that for one single atom, it really is a really minuscule amount, right? One atom isn't that big, right? And pulling off one electron, not super impossible. So what we do in the definition is we add a few little technical notes. Yes, we are trying to pull off that electron, but I'm not just going to do that for one single electron. I'm going to imagine lining up an Avogadro number, or a mole of atoms, and I'm going to imagine doing this process of pulling off this one electron off of a mole of atoms. So remove an electron from a mole, right? So I'm going to line up an Avogadro number of them. Also, the state matters. So whether this is solid, liquid, or gas, that's going to have some impact on what the particles are actually doing, how the particles actually look like, and interact together with intermolecular forces. We're going to specifically be looking at gases. So from a mole of, usually they say gaseous. Gaseous just means gas. I'm going to use the word here species because sometimes it is an atom that's neutral, no charge. Sometimes it's already been charged and is an ion. Species is a more general word for thing or substance, particle. Okay? So from a mole of gaseous species, all of them have to be at ground state. So this is usually a 2-mark question. Most people remember, yeah, ionization energy is the energy to ionize, it's the energy to make it charge. In this case here, by removing electrons, I'm making it positively charged. but the thing you need to remember here is this technical detail, you're doing it for an Avogadro number and it has to be a gas. So let me do what's called a representative equation. Sometimes when people see the word equation, they start thinking math. In this case here, equation just means balance equation. So if I take an element, let's call it M for now, I do want to be reminded this one here is a gas, so it is incorrect if you don't put this gas here. And what I'm going to do to this element here, this one here will have some number of shells, this one here will already have some electrons, they may be in different orbitals. And again, all we're going to do is we're going to grab the first electron that we see in that order PSDF and try to basically remove this electron from the atom, not just from one, but from a mole. If I pull off that electron there, you'll notice I'm not touching the nucleus. The nucleus is where I have my protons. The nucleus is what's making me this element M. So in this case here, I'm still going to be M. But in this case, because I've lost an electron, the electron has taken away a negative charge. This M here has what's been called oxidized. This M here now becomes the positive charge ion. So M plus, it's still going to be in the gas state, and that free electron is now free to go. That electron ends up, we say, leaves to infinity. As long as the electron is still in the vicinity, close by the positively charged center, they will have some potential energy. Once this ionizes, we say it goes to infinity. We say it's completely gone, completely erased from the picture. That one there, if you manage to do that, is going to be called the first ionization energy, right? Because that's the first electron that it took off. Now, for an element that has more than one electron, most elements do, if I come back, I grab one of these other electrons, maybe it was already there, and I remove another electron, that one there would then be referred to as the second ionization energy. This is the second time I've come back to actually remove an electron. So we've already removed the first one, so I already am at M plus 1. We are still in the gas state because of this technical note here. It has to be gaseous. We're going to remove one more electron, same pair of tweezers, but I grab yet another electron, and now we become even more charged. You want to be careful, every time you ionize, it's only for one electron. When I start putting numbers to this, if you had to guess, which one do you think is going to be bigger? The difficulty to pull off the first one or the difficulty to remove the second one? If you set the second one, you would be correct here. Although even with a simple Bohr model, it looks like these electrons are on the same shell out. As I remove this electron, I'm actually removing a little bit of the electron repulsion. Say I had 6 electrons like carbon before, as I remove that first electron, I only have 5 electrons left. Those 5 electrons still hate each other, they still push each other away, but there's going to be less repulsion than in the case I had 6 electrons. So every time I remove an electron, sure enough, it actually does shrink a little bit. The second shell ends up being a little bit closer to the nucleus. So it should be a little bit hard to remove. The nucleus has a stronger, tighter hold on things that are closer than it. You need to pull harder. So let me just put some numbers to this. I'm totally making these up. Let's say the first ionization energy for this metal here is 10 kilojoules. Usually they'll just write it like that. So kilo means 1,000 joules, so 10,000 joules. Because again, in the technical definition, we said we're not just doing this to a single atom. I've gone to an Avogadro number. I've gone to an entire mole, a string of these atoms here. This 10 is the energy you need to remove an electron off each of those atoms in the mole. Usually you'd say 10 kilojoules per mole. And maybe second ionization is going to be, 100 kilojoules per mole. Right? Remember this number, this ionization energy is basically a measure of how hard is it for you to try to pull to completely get rid of this electron. In this case here, you see that the 10 is a relatively small value. It's relatively easy to remove the electron. As I pull off that electron there, because of the less repulsion, because the shells are a little bit closer, when I come back just for that second electron, I need to pull a little bit harder with this pair of tweezers. It's a little bit harder. Be really careful when you look at these numbers here. Sometimes people say, oh yeah, this number here is bigger because I'm trying to remove both electrons. That's not true. You'll notice in these questions here, first ionization was to get rid of the first electron. Notice the first electron is already gone when you then apply an additional 100 just to get the second electron. So every time you end up trying to move an electron, there's a separate ionization energy term. In chapter 3, we're going to see in our data booklet, it basically lays out for you each element with the first ionization energies. These are all quoted. And then chapter 3, we're going to look at some trends that we're introduced to. This notion of coming back again and again for ionizing here is typically called successive ionizations. The word successive means one after the other. So let's just write down the words here. Successive ionizations become harder. If you want to do the language here, this is going to be successive ionizations will have a higher ionization energy. The difficulty to remove the next electron becomes harder and harder because the radius decreases. Radii is plural for radius. Okay, the size of it decreases. There were a couple reasons for this. Okay. So far we've said, well, for carbon, it had a bunch of electrons with shell number 2. Because I've removed an electron, there's going to be less repulsion between the leftover electrons. So radius decreases. It could be there's less electron repulsion between the remaining electrons. Because it shrinks a little bit here, we're going to learn the Coulomb Law in tomorrow's lesson. Basically, when charges are closer together, the force of attraction, they see each other better, and basically it makes it harder to pull off. Another reason why the radius would decrease, every time I come and ionize it, it becomes more and more positive. So not only am I losing that electron and I'm already shrinking, now that I'm n+1, because I'm positive, I'm going to have a stronger attraction to that next electron. There's more of a net positive charge here, there's an electron charge here. Because I'm increasingly getting positive, that's another reason why the radius would decrease. So in this case here, another aspect here, the ion is more positive. After the first ionization, you're +1, then you come second, you're trying to move an electron off of +1, it's harder, right? It's more attractive. And the one I haven't introduced yet here is, especially as we come back time and time again, because electrons are on different shells here, let's say I do first ionize, second will be harder, third will be harder, fourth will be harder. What if I came along and removed the fifth electron? For the fifth electron, after I remove that fourth electron, the second shell is completely gone. I've suddenly gone from having a radius of being 2 shells out, and now I'm only a radius of being 1 shell out. Because these electrons here are a lot closer to the core, you're going to need to really get a tight hold on this electron, really pull hard to get rid of this electron. And in fact, there is going to expect it to be the biggest jump, because suddenly these were all roughly the same because they were all on shell number 2, but suddenly on shell number 1, because we've lost a shell, there's a dramatic distance change, and therefore there's a dramatic change in ionization as well. So fifth ionization, so that's sort of probably the more important. Why might the radius decrease here? We may have also lost a shell, depending on how many valence electrons that I had, and typically there's another case here. Because we're doing ground state, every time I revert down to a lower shell, I actually end up trying to remove electrons off the full shell. We know noble gases are stable because of that full shell. They're going to try to resist it as much as they can. So the radius decreases because I've lost a shell, and we're trying to remove from, I'm just going to call it full shell stability, like a noble gas. So for all those reasons, we would expect these numbers here to increase. So this one here actually becomes a nice evidence that we actually have different subshells. So I'm going to just plot out for you here. I'm going to plot out for you ionization energy against sort of which ionization I'm doing. So first ionize, second ionize, and whatnot. Let's take a look at an element, say sodium. Just start off with your regular Bohr model picture. So you do the 288. We still do this exactly the same, even though now we know the electron configuration model. And now what I'm going to do is I'm going to plot for you how hard is it, the ionization energy, versus which electron am I pulling out. So we start off, say the first ionization energy, first electron is going to be that 3s electron. It's the one on the first shell, on the third shell. Really easy to remove because this one here is the furthest away from the sodium. So I'm just going to randomly put a number. This one here is relatively low energy. Some number I'm going to make it up. Let's say 10. As I come back for the second electron, because I first ionized, because sodium has lost its shell here, the second electron that I come back for has to be on shell number 2. In fact, it has to be on a p kind of electron. That shell number 2 is a lot closer than, say, on shell number 3. The second one will be significantly harder than that first one. So when I go to the second ionization, maybe I'm up to that 100. Maybe I'm up to significantly harder. Now, as I go through here, if I actually look at the configuration, so 2s and 2p, we'll notice those electrons that we have here. I just removed one of these electrons on the second. The next one is going to come off also a p shell. It is going to be harder because there's less repulsion, but it's not going to increase as dramatically as the first case. In fact, for these 6, it's not going to increase that wildly. So between 2, 3, it's going to be sort of up and down like that a little bit. By the time we get to the s electrons, because of the shape, they're a little bit closer, they're a little bit lower energy than p's, we will get a little bit more dramatic distances. Oh, the s electron is harder to remove than the p electron. We'll see this. Yeah, there's going to be a steady increase. It may even zigzag back and forth. And that's sort of inconsistent with the Bohr model picture. With the Bohr model, if all 8 electrons were all identical, I'd imagine a more linear trend here. After I manage to remove all 8 electrons, if I then start going into the first shell, again, this one here is going to be a lot closer to the core. This is going to be significantly harder. Again, I'm going to expect to see a very big jump. So in fact, what we have here is we have sort of this was on n equals 3. This was furthest out. This is on n equals 2. Once I lost all those electrons, and now I'm on n equals 1. The inner shell is also full, significantly harder to get. If I actually plotted this here, sometimes I actually plot this on a logarithm scale, because sometimes these jumps are so dramatic that if you did a regular scale of it, it actually would be a graph that's really, really tall. So let me just put some numbers to this, an example of how they can ask this. Let's imagine here successive ionizations. Successive ionizations for, let's do X as a gas. Typically they use M for metals and X for non-metals. Let's say I give you a few numbers. First ionize is 20 kilojoules. Second ionize is 210 kilojoules. Third ionize is 3,500 kilojoules. Fourth is 4126 kilojoules, something like that. Okay. So at least for this element, at least you have to have 4 electrons, because I managed to pull off it 4 times. What this question is going to ask you for is which group, where would this element probably show up on the periodic table? Which group might this be? So is it an alkaline earth metal? Is it a halogen? What is it? And in this case here, although we have that gradual trend, typically the ionization energy increases. It gets harder, i.e. increases, and it becomes more difficult every time you come back. What we're going to look for are actually these really, really steep jumps. Between pulling off one electron versus the next electron, there's a significant difference, because when there's a significant difference, that's probably when I lost the shell. So what you're going to do as you're looking at these numbers here is you're just going to track the distance, just roughly. So 20 and 210, I think it's 190. This one here I know already is the biggest difference. 3,500 minus 210, 3290. You'll notice 4126 is bigger, but if you just look at the difference here, 4126 minus 3500, it's not that much more than the one previous. So what's going to happen here is you're going to look for when did this biggest jump occur, because when the biggest jump occurred, I probably lost the shell during this big jump. So this second electron was probably the very last electron in that shell. I lost the shell, and then when I come back, in this case here for the third electron, sometimes this biggest jump occurs between the first and second, sometimes the third and fourth, and whatnot. But whenever there's a big, big jump, you would expect I probably lost the shell. It took me 2 electrons before I lost the shell, so I would expect to be an element, let's say X. I don't necessarily know how many shells I have in total, but I would expect first one, 20, easy. Next one, 210, also relatively easy. The third one, oh, because I lost that shell here, for my third one, it's significantly closer to the nucleus, really, really hard. You really need to yank on this electron, and this one here won't come off. So that just introduces the ionization energy in general. We're going to take a look more so in chapter 3. Let's just look, this was successive ionizations. This was taking one element and removing electron one after the other. What we can do is we can actually track this on the periodic table. We're going to do this a lot in the 3rd chapter. What we're going to do this time is we're just going to compare first ionizations. So this time I'm not coming back a second time for the next electron. This time I'm just comparing pulling off one electron for different atoms. We will look at radius and trends later in the week as well, but in this case here, if you just remember your sinus 9, sinus 10, just even from Bohr model, we know, say, hydrogen only has shell 1, right below it, lithium here has shell 2, sodium here has shell number 3. what's happening to the radius as we go downwards? Because we have more shells, I would expect that the radius increases. Again, radii is plural for radius. Because the size is gradually going from small and we're gradually getting very big, all of these guys here have some number of electrons, and all I'm doing this time is I'm trying to remove one electron off each of these elements. This hydrogen here, because shell number 1 is really closely tied to the core, I would imagine this electron is really hard to remove versus something like francium or cesium down here, because the same electron I'm trying to remove, because it's so much farther away from the core, I would expect this to be easy to move versus this one here to be harder to move. So based on a periodic trend, as the size itself gets bigger, I would expect that the ionization energy actually decreases in the direction that I drew. So it gets easier and easier as the size increases. A little bit harder as we go across. As we go across, let's first look at radius. What do you think is going to happen to the size of the element as I go across? What you're going to find when you compare the Bohr model, as you do your lab as well, you're going to see, well, as I go across, it's not like I pick up an extra shell or lose a shell. Let's say I'm on shell number 2, this row number actually tells me how many shells the Bohr model has. Everything on shell number 2 has 2 shells. Remember, we did that question though, just because we have 2 shells doesn't mean the 2 shells are necessarily the same distance away from the core. In fact, what's happening as I step over from lithium, 3 protons, to beryllium, 4 protons, to boron, 5 protons, as the core itself gets more and more positive, as I add new electrons to shell number 2, they're going to inevitably get pulled closer and closer to the nucleus. So this atom here tends to shrink as you go across. It's actually fairly notable. Again, in your data booklet, it shows you the numbers for these radius as they're dropping. And again, what we can say here, the radius tends to decrease. Radius decreases. The language we're going to use is across a period. The word period just means row or a horizontal line. And in this case here, I assume across means we read left to right. So as I head to the right, based on the direction that I showed you, as the size of it gets smaller, you're coming in and you're removing that one electron off all these ones here, and you realize then, oh, because the noble gas has a very tiny radius, it should be much harder to remove than say the alkaline earth level. So ionization energy increases as I go to the right in this direction. So it becomes harder. We're going to see a lot more of these periodic trends in the 3rd chapter. As I mentioned, the reason why it's showing up in this chapter is just like with any good rule, with any good expectation, there's always exceptions. So I'm going to do 2 exceptions with you. First exception has to do with 2 elements up here. We're going to compare nitrogen. Nitrogen is going to be group 5 or group 15, and oxygen. Based on my periodic trend, I would have expected nitrogen is a larger atom, oxygen is a tinier atom. Right? Nitrogen only has 7 protons, this one here has 8 protons. We would have imagined that, just like we said, the ionization energy for the one on the right should be harder. Oxygen should be harder to pull off. As an exception, however, this is how the question is going to be worded. Why is the ionization energy for oxygen lower than for nitrogen? Again, this is against the trend that we expect. To answer this question here, we may go to our trusty electron configuration model. So let's draw an energy level diagram. 1s, 2, 2s, 2p for nitrogen. And then if I did the same for oxygen on this side here, also 1s. Remember, the energy spaces between the elements will be different. Right? That's characteristic of the element, but at least the relative order is the same. For oxygen, it's going to be 1s2, 2s2. We do our Heinz rule, we have this. And based on the statement that they've made, they've said oxygen's electron is easier to remove. It's easier to pull off. Let's figure out which electron I'm removing. Maybe we pull it off PS and then DF. In the oxygen example, I'm trying to pull off this P4 electron, the 4th electron into that orbital. Whereas for nitrogen, I'm trying to pull off this one. Why might it be that even though size-wise, I would expect oxygen has more protons, the electrons are closer to the core, it's harder to remove, why might it be that in this case, the electron is actually easier to remove? 2 comments that you can say here. First thing here is, these 2 electrons, I know I've switched these 2 electrons together. Do these 2 electrons like each other? Because all electrons here have a negative charge, yes, it's like being put in a room with your worst enemy, right? You don't really want to be there, but the compromise is at least we both get too close to the nucleus. Given an opportunity, if you come in with a pair of tweezers, if I grab this one here, this first electron says, yep, take him. I don't really like it. So in that case there's going to be extra repulsion. So extra repulsion because those two electrons are paired up. Or you can argue on the nitrogen side here, why might it be so hard to remove this single electron? I know we didn't quite get to doing an exception with this, but this should remind you of the chromium case. Remember, chromium was more stabilized because it had a perfectly half-weight shell. Out of the 5 d orbitals it already had 4. Chromium had promoted less electron up. In this case for nitrogen, it's not dramatic enough for us to promote this up, but definitely we still are enjoying the half-weight stability here. So nitrogen here doesn't really want to lose this electron because it has a stability for having 1 electron piece. So not impossible for you to remove this electron, but the second that you get rid of this electron, I now no longer have my half-weight stability. I'm now no longer as stable. So with our electron configuration model, we were actually able to explain this exception. There is one other exception that's a little bit less convincing, but we're going to argue it the same way. Let's figure out why is boron's electron easier to remove than boron. So these are the two exceptions they want you to know from this chapter here. The same exception applies to elements that are right underneath it, because that would also be a P3, that would also be a P4. In this case here, if we compare boron and beryllium, boron is sitting right here versus beryllium is sitting right here. It would also apply to, I believe it's aluminum and magnesium. Okay. These are exceptions. Based on our trend, we said the size is supposed to shrink as you go across. As you shrink, it should be harder to remove off a smaller one. And yet in the statement, it says boron, which is on the right side. So beryllium was here, boron was over here. I would have expected boron to be a tinier element. I would have expected this to be harder, and yet they were kind of mixed. Similarly speaking here, we're just going to start off with the electron configuration. Figure out for yourself which electron I'm going to try to remove on both of these cases here. In this one, I already have a full 2s ring. In this one, I'm actually not pulling it from the 2s. In this one, I'm already starting to pull it out from the piece. So in this case here, what's being unfair? Because we do have those sublevels, I'm actually removing a p electron from this one. So remove a p electron versus the other case here, I'm trying to remove an s electron. Because those subshells are different, they relate to their shapes. You can say p electrons are easier to remove, and you can quote just sort of the spatial orientation of this here. The 2s is spherical, it sort of marks out the circular region, and 2s is kind of circular in nature, whereas when I get to the p orbitals, those dumbbell shapes, there's at least parts of the p orbitals that are farther out in the 2s. Again, because we're farther out, it's going to be much easier to remove. So, p electrons are easier to remove, and that would explain that exception. One other note here, because the s's and the p's are the outermost electrons, only s and p count for valency. So for the Bohr model, which only shows your valence electrons, the ones that do the bonding, those are the outermost electrons, s's and p's. The d orbitals and f orbitals, which we sort of skipped over some of the shapes yesterday, we're going to find that no matter the shape, some of the d orbitals look like butterflies. I'm just going to draw one of them for you here. The d orbitals, although they are higher energy, and the f orbitals, I'm not going to bother drawing them, the f orbitals are also higher energy. Spatially speaking, when you actually look at the wave function, when you actually plot out where those regions are, you actually find that those regions are a lot closer. So B's and S, yes, they are actually higher energy, but they are always held closer to core. They're inner orbitals. They don't do the same type of bonding as the S's and P's. So if ever they ask you for valence electrons, how many electrons should the Bohr model show? The Bohr model only shows the S's and the P electrons. So if you have any questions, just let me know. We're going to slowly transition to chapter 3. Fortunately, there's a lot of overlap between 2 and 3, and then see to your test. Take care, guys. See you later.